Great, thank you. Good afternoon. My name is Steve McLeod. I'm the current president of the Coastal Society and an environmental scientist with the environmental consulting firm WSP in Buffalo, New York. Thank you for joining this session of TCS's Coastal Connections web conference series. The trending topic we will cover today is the art and science of projecting sea level rise, for which our presenters will examine historic and recent trends in comparison to future sea level rise projections. Please note that the session is being recorded and the recording will be posted on the TCS YouTube channel in the coming days. For our non-member guests, the Coastal Society is a nonprofit organization founded in 1975 with a mission of fostering dialogue and advancing education to promote the wise use of our coastal resources. You can learn more about TCS and become a member at www.thecoastalsociety.org. The Coastal Connection series is meant to better connect TCS members and guests from the coastal community throughout the year. Our intent is not just to be educated by our expert guest panelists, but also to see and hear from you, our other participants, during the Q&A discussion later in the session. We encourage you to turn on your camera and share your questions and thoughts at that time. Special thanks to Ashley Gordon and Melanie Perello for their support in organizing and running this session. Ashley, are there any other logistical points you would like to make at this time?
No, thank you, Steve. I think that covers everything.
Okay, great. Then now I am happy to introduce our moderator for today's session, Whitney Gray, Resiliency Program Manager at Michael Baker International. Whitney is a fifth-generation Floridian who worked in the Florida public sector between 2008 and 2021 before joining Michael Baker. During that time, she helped local, regional, and state agencies to identify and address the vulnerabilities of their communities to flooding and sea level rise. For example, in 2012, Whitney joined the Florida Fish and Wildlife Conservation Commission as the first ever sea level rise coordinator, serving as a subject matter expert on the effects of sea level rise on coastal ecosystems and species. Whitney later joined the Florida Department of Environmental Protection to establish the Florida Resilient Coastlines Program. In 2018, Whitney also spearheaded the creation and publication of the Florida Adaptation Planning Guidebook, a roadmap for vulnerability assessment and adaptation planning based on research specific to Florida. In 2019, Whitney further led the effort to implement Statute 161.551, creating the SLIP, that is the Sea Level Impact Projection Rule, an online tool for compliance in regulatory matters. This represented the first time the state of Florida recommended a specific sea level rise projection for planning infrastructure. So no stranger to the potential effects of sea level rise and ways that we might adapt to it. At this point, I will turn it over to you, Whitney, to further introduce our guest speakers.
Thank you so much, John. Steve. I've got John Englander in my brain. So thank you very much for that introduction, Steve. It's great to be here. Thanks to everyone who's joined us today. I'll introduce both of our speakers right off the top. And as we go through the presentations, if you all would please hold your questions till both speakers are finished, then we'll have a nice long question and answer period afterwards. So jot down your questions as we go along. Our first speaker today will be Dr. Molly Mitchell. Dr. Mitchell is a research assistant professor at the Virginia Institute of Marine Science, or VIMS, and Molly's research interests focus on shifts in coastal resources due to the interaction of sea level rise and human-driven changes. Although primarily an ecologist, Molly works on projects involving physical dynamics like sea level rise trend analysis and shoreline geology, and human decision-making, social vulnerability, sea level rise adaptation, adaptive management application, and so on. Molly's recent projects include developing sea level rise report cards that provide trends and projections to aid in coastal planning. Molly's research is meant to be applied by planners on all levels and across resources She works with representatives from many different groups to help translate research and current scientific understanding into practical recommendations. She received her PhD and master's degree in marine science from VIMS and her BS in biology and environmental science from the College of William and Mary. So we welcome Molly to our talk today. Our second speaker will be John Englander. John is an oceanographer, a multi-book author, and an international speaker on climate change and sea level rise. With many expeditions to Greenland and Antarctica under his belt, he has seen the devastating effects of accelerating polar ice melting firsthand. His first expedition to the high Arctic was diving under the polar ice cap in 1985. John's best-selling first book, High Tide on Main Street, established him as a leading authority on rising sea level. His recent book, Moving to Higher Ground, Rising Sea Level and the Path Forward, explains why sea level rise cannot be stopped and our options. John is a fellow of the Institute of Marine Engineering, Science and Technology, UCSC, Institute of Marine Science, that's University of California, Santa Cruz, and of the Explorers Club. His presentations about sea level rise are widely acclaimed for putting the science into plain language that can be easily understood. So I hope you'll welcome both of our speakers, and please do remember to mute your microphones. And Molly, I'll turn it over to you.
Thank you very much. Thank you for that introduction. They're perfect. Thank you. Okay, so today we're talking about projecting or really forecasting sea level rise. So this is a street in Norfolk on a beautiful sunny day. And you can see I'm actually about 2 blocks away from the water when I took this picture. Not only do we have water up on the street, we also have some wave action going on there. And so this is becoming a much more common occurrence in a lot of places in the United States. And flooding is becoming a much bigger concern. The rate at which flooding is increasing is accelerating. So this is, over the past 20 years, has become a big concern. Over the next 20 years is going to become an even bigger concern. So today we're going to look at different ways of how we forecast how much that change is going to be. Okay, so there's kind of 2 ways of approaching this problem. One is to use empirical data. So these are historic measurements of what sea level has been like in the past, and then looking at trends and changes in that data. We can either get empirical data from tide gauges, which is a local picture of what's happening. And if we want a bigger picture, we need to put lots of tide gauge data together. Or we can get it from satellite altimetry. And that actually covers the entire globe, so we can get a more global picture of that. And what we can do is we can look at the change in sea level over time. How long time we have depends on which method we're using. Tide gauges date back to the mid-1800s in some harbors in the United States, but there have been a lot more of them since the 1980s. And the satellite data dates back to 1992. So we can calculate those trends, and based on that, we can extrapolate to the future what we expect that to be. So what are the pros? The advantages of the empirical data is that it is location specific. It doesn't require us to really understand what's causing sea level. We can just measure that change in sea level. It can highlight the impacts of decision making. So in places where we can control aspects of what's driving sea level, we can actually see in the history where those decisions have changed the trajectory. The main con to this, though, is that this assumes that the future and the processes going into the future closely align with the past. And we know that's actually not a great assumption right now. So really, if you're going to take empirical data and use it to move forward, which is most of what I do, you can only limit your forecast to about 30 years in the future. You can be pretty comfortable within the next 20 years, maybe and out to 30 years of what sea level is going to be like. But beyond that, it's really not an appropriate measure. So what if we need to know more than 30 years out in the future? If we want to do that, we need to turn to what they call process-based models. So these are global models of how we understand the world works, and it connects all the different pieces. And we can use this understanding of the connections between the processes to drive the global change in sea level. Okay, so it gives us a mean and average global change in sea level. The big advantage of this is not only can we move out further in the future, it allows us the consideration of different futures. So we can say, what if? What if the ice sheets melt faster than we expect them to? What if the ice sheets melt slower? What if temperatures warm more than we expected? So we can look at all these different what if scenarios and see how they affect future forecasts of sea level. The main drawback to this is that this is giving us that global mean average. So when we want to get back to a local area, when you want to know what's happening in your town, we have to downscale that model. And it really requires understanding all of the processes and connections that are driving the sea level at that local scale in order to do that downscaling appropriately. Okay, so these are the two ways we get empirical data. So this is a tide gauge. A tide gauge measures what we call relative sea level rise. And that's the experience of a person standing on the shoreline, or it could be a house that's been there for 30 years. So it is measuring all the different processes that are occurring together. And that includes sea level rise, global rise, and ocean dynamics, changes in ocean dynamics, and also land sinking or subsidence, or land elevation through tectonic uplift. So any of these are captured in your tide gauge record. So your tide gauge is telling you what that spot is experiencing. Satellite altimetry is a little different. It's measuring the sea surface relative to the center of the Earth. But the satellite altimetry, so we have tide gauges just mostly in harbors and then key navigational points. But the satellite altimetry can cover the entire globe. And so this is the result of a trend analysis for the satellite altimetry from 1992 to 2013. And one of the important things I want you to take away from this is that we talk a lot about mean sea level. Okay, and so you'll see in the newspaper, sea level is rising 3.2 millimeters a year. But it's not a bathtub. That's not uniform across the surface of the globe. So what we can see here is that these dark red areas are rising 8 to 10 millimeters a year. And these blue areas are falling 2 to 4 millimeters a year. So we get significant differences in how sea level is responding in different areas due to changes in ocean dynamics and ocean temperatures. Okay, so if we look at the relative sea level rise, so if we take a tide gauge and we look at what's happening here, we can take the trend over time. And this graph is showing us, this is from a tide gauge in Sewell's Point, Virginia, which has one of the highest, it's the 4th highest rate of rise of the 32 stations that I do the report cards for. And you can see these blue lines with the little dots at the top. These are the monthly mean sea level that was observed at that station by that gauge. So this is data. The dark blue line is just the underlying signal of change that those monthly mean sea levels going through. So what we can see is that there are months when sea level is running high, and there are months when it's running low. And there are also years where sea level is running higher and years where sea level is running lower. So this orange line is the trend going through that signal. So this is our average sea level change over this period of record, so from 1970 to 2020. The orange dotted lines are sort of their confidence intervals. What they're telling us, they contain 95% of the data. And what they're telling us is that this is a height which is not unusual for the monthly sea level to reach in some years. And this lower line is a level which is also not uncommon for it to reach. So we see these cycles going on and off, and we know going into the future, we will have something that looks like this too, okay? So we always show graphs with just a single line, or even worse, a single number. We're gonna have 0.5 meters of sea level rise, okay, in 2050. But what we actually know is that there's a lot of variability annually in where we are around that mean trend. So that's really important as we go to move from our sea level rise projections into actually using them and implementing them on the ground. And I'll come back to this point and show you a little bit how that affects our decision making. Okay, process-based models. So these are the big global models that are in the IPCC reports and the National Climate Assessment reports. And these take our understanding of how the changes in carbon affect all these other properties, so ocean circulation and ice sheet melting and ocean temperatures, and then what that does to sea level rise, okay? So these give us, again, that global mean level, and then we have to downscale it. So these process-based models are predominantly driven by changes in greenhouse gases. And so when we set up scenarios to use these global models, we're looking at sets of trade-offs. And these are kind of a simplification over on the side here, but this is the idea that we're saying, okay, what if we invested a lot in low carbon types of energy, and we decreased the density of people living in an area, and we planted more trees, which we know take up carbon, or we put a lot of electric cars on the road. So what if we made this set of decisions? Or what if we made a different set of decisions? And so these are called shared socioeconomic pathways. And each of these pathways you take affects the amount of greenhouse gases that are in the atmosphere, which in turn affects the temperature of the ocean. As water heats up, the molecules move faster. And so they start to actually take up more room. And that is why a pressure cooker works. Okay, it's that same principle. In the oceans, what's happening is as that water starts to take up more space as it heats up, it expands and expands onto the land. And so the faster it heats up, or the more it heats up, okay, that's gonna make sea level a little bit higher. The other thing that really affects these scenarios here is the rate at which the ice sheets melt. So the faster the ice sheets melt, then the faster we reach a higher level of sea level, okay? So each of these scenarios assumes that there's some combination of decisions that leads to some amount of carbon and other greenhouse gases in the atmosphere, and that affects the temperature of the ocean, and it affects the rate at which these ice sheets melt. And so this gives us a lot of different possible futures, right? So we don't have just one projection of what sea level will be. We have a number of different projections. This is really important in planning because we know there is no single future out there, and that the decisions we make do impact the future. It is, however, a challenge for planning because now you're planning for lots of different possible futures. You don't know which one is right, and there's no way to know that for sure. The one thing I do want to point out is that under any of these scenarios, sea level is rising. Okay, so that's the part we can be sure about, that sea level is rising. The rate at which it's rising is the part that is that depends on the decisions that we make. Okay, so this is a downscaled global forecast. This is NOAA's 2022 report. They just put this out. This is for Sewell's Point. So this is the same station that I was showing you previously. And these are the 5 scenarios that NOAA is currently using. The numbers here refer to the global level reached by 2100. But basically, this is the low scenario, the intermediate low, the intermediate scenario, intermediate high, and then the highest scenario. For reference, I've put, this is the tide gauge forecast that I showed you on the couple slides ago on there. And so what you can see is that there's a lot of possible futures. The big thing to take away from this is that the tide gauge is suggesting that if things continue the way they have been in the past, that this is the amount of sea level we would expect to see in 2050, which means that any of these scenarios down here probably require some drastic changes in our decision-making to get there. So this one is a scenario which might occur if things speed up, if processes speed up, right? But to get to these lower ones would require processes to slow down. So this is one of the important things about the historic data, is it does give us a metric of how we're progressing along the way and how important different decisions might be. Okay, so these are the tide gauge 2050 projections for the 32 stations. All the names don't show up on the graph, but there are actually 32 stations along the East Coast, Gulf Coast, West Coast, and Alaska in the United States. This dotted blue line is the IPCC's 8.5 scenario. So this is one of the higher relative concentration pathways that you can go down, the shared socioeconomic pathways. And so this is the global average, okay? So not for any particular station, it's for the globe as a whole. So what we can see is that in the United States, the East Coast and the Gulf Coast are both running quite a bit higher than that global projection. The West Coast, less so. And then Alaska, there's a lot of tectonic uplift on these stations in Alaska in these particular areas. And so sea level is actually falling relative to the coastline in these areas where the coastline is being lifted up. All of these stations above this zero line here, sea level is rising, but the rate at which it's rising varies a lot. And whether or not that rate is accelerating also varies. So the West Coast, there's not a ton of evidence of accelerating sea level rise at this time, although the global models suggest that it will accelerate. But on the East Coast and the Gulf Coast, sea level rise is accelerating quite strongly at many of the stations. So what's driving this variability? We're going to talk a little bit about what processes would affect that variability. Okay, so on the East Coast, in addition to that global sea level rise caused by increased temperature and melting of ice sheets, we also have changes in a dynamic circulation system called the Atlantic Meridional Overturning Circulation. And this is a system called the conveyor belt, where water heats up in the tropics and it comes up along the coast of the United States. Right here, we call it the Gulf Stream. Right about the mouth of the Chesapeake Bay in Virginia, it takes a turn, goes out into the center of the ocean. Some of it returns back down to the tropics. The rest of it comes up off the coast of Europe and then up near Greenland, where it mixes with melting ice off of the ice sheets. It cools. Cold water is more dense than warm water, so it sinks, and it's returned to the bottom, back to the tropics on the bottom of the ocean. And so this cycle just goes over and over and over again. However, it has been slowing down lately, and the climate model suggests that this could slow down by up to 30% or even possibly reach a threshold where it becomes unstable and completely breaks down. And so this affects the temperature distribution or climate, okay? So one of the reasons why England has a more moderate climate than, say, Nova Scotia is because of this warm water that's coming up and affecting the atmospheric processes there. So this can have big implications for the temperature distributions around the globe. But it also affects sea level, and this is the way that it works. So this is from a paper by Ezra and Atkinson in 2014. And what they found was that the Gulf Stream, this is where it was located in 1996 to 2003. And over time, it has moved offshore. And as I said, it's slowed down. What does that do? Well, it turns out as the Gulf Stream moves past the coast, it actually draws water with it. And so if you were to go out into the ocean on a boat and you were on top of the Gulf Stream, you'd actually be higher elevation than the water right in front of the coastline. So there's actually this kind of hump of water out in the ocean, that's the Gulf Stream. As it's slowed down, it doesn't pull as much water. So that hump has gotten lower. And the water, this gradient here is relaxed and is coming up higher on the shoreline. So this is one of the things that's happening along the mid-Atlantic and North Carolina coast that's driving high rates of sea level rise. One of the other things that affects variability is something they call ice sheet fingerprinting. And this is the idea that we have these melting, this is the Greenland ice sheet, okay, is melting. And these ice sheets are so big, they actually have a gravitational pull to them. And as they melt and become smaller, that gravitational pull is relaxed. And so this water had been drawn up towards Greenland is now relaxing. So that means if you're looking at how much things are changing, the areas closer to Greenland are changing less fast than you would expect, and the areas further away are changing more quickly than you would expect. The same effect can be seen with the West Antarctic ice sheet and the East Antarctic ice sheet just at the opposite pole. So this one is affecting the United States. The Greenland ice sheet is affecting the United States much more strongly. And so what this means is anywhere that's blue, you're actually seeing less sea level rise than you would expect. And anywhere where you're moving into these other colors, you're starting to see more sea level rise than you would expect from this relaxing. And then vertical land movement, subsidence, or tectonic uplift are the other main process that's happening. This one is always interesting to people because some of it is under our control, some of it is not. So tectonic processes, so that can be either the uplift or one of the big ones is glacial isostatic adjustment. And this is where there used to be really big ice sheets back in the last ice age on the top of Canada, New England area that depressed the land, the crust below it. And so what happened is, if you think of this as being New England over here, as this part of the crust was pushed down, Virginia actually would bulge up. So sea level was falling in Virginia relative to the land. This ice sheet melted, and very, very slowly, the land has been rebounding. And so what that means is that the land is going up a little bit in the areas where the ice sheet was at the end, and it's coming down a little bit in Virginia. Okay, so for a person standing on the land, we combine the subsidence with the actual rise in sea level, and we get a higher rate of relative sea level rise. There are some other processes that can affect it. This is a crater from a meteor thousands of years ago, and the fractures on the edges may affect to a certain extent the rate at which subsidence occurs. The other big one is groundwater, or even more so hydrocarbon withdrawal from the ground. So groundwater and hydrocarbons take up space in the sediments, and as they're pulled out and used, the sediments above them collapse. So when this happens, we have localized land sinking. And this is an example from Virginia, where they've looked at the rate at which land is sinking across the road. And the important thing about these groundwater and hydrocarbon withdrawals is, one, they are something we can manage. So they're very interesting to people from that aspect. The other thing is that they can vary quite a bit on very short distances. So this shows that there's across very short distances, 5 kilometers, you can get quite an increase in subsidence rates. But when you stop withdrawing it, they see recovery very quickly usually. So the subsidence rate stops. All right, so the last thing I just wanted to share is how this all affects the kind of local experience that you see. So we have our rates of sea level rise. This is Baltimore, Maryland, and this is Sewell's Point, Virginia. They're both in the Chesapeake Bay, but rates of rise in Sewell's Point are higher in Norfolk than they are in Baltimore. However, arguably Baltimore has the bigger problem. Why is that? So Sewell's Point in Norfolk, they have a much higher tide range than the tide range in Baltimore. And if you think of it this way, okay, so if you're going to build your house, you're going to build your house in a place where it doesn't flood every day, right? So you're going to build it above mean high water. Ideally, you're going to build it above HAT, which is the highest astronomical tide predicted in a 19-year tidal datum. Okay, so as sea level is rising, because we already had this big tide range in Norfolk, sea level is actually coming up relative to the tide range, not as much in Norfolk as it is in Baltimore. So houses in Baltimore are built closer to an area that will be underwater in 2050 than the houses in Norfolk are. So there's this connection between the tide range and the sea level rise rate, and also the elevation of the land into what you're actually going to experience. So the places with the highest rate of sea level rise do not necessarily have the biggest problems. It depends a lot on how we use our land, how we distribute our population around that land. So some considerations when we think about sea level rise and we want to take this into management. We talk a lot about mean sea level, which was developed in the 1983 to 2003 tidal datum for most of the stations in the United States. This is mean sea level back at that time. This is where our mean sea level is trending today. You can see that what we call mean sea level is becoming increasingly less relevant. And these projections show the line. I said it shows mean sea level, okay? So first of all, daily water levels exceed these values, right? Because the tide comes in and comes out. And we have this dynamic signal that's going to occur, okay, that we know is predictably going to be probably between these two lines. There may be months when it's above these lines or below these lines, but generally it's going to oscillate between these two lines. So what does that tell us? It tells us that although we say sea level will be 0.5 meters higher in 2050, at some time in that 2050 range, that high tide will be at this highest point within the envelope that we can see, plus the half of the tide range, right? So the high tide could be 1 meter above current mean sea level. And a large storm is going to bring in even higher water levels. So these are the important considerations beyond just those mean sea level forecasts that we need to consider. So thank you. I'm going to turn it over to John now, and then we'll take questions at the end.
Let me just say while we're transitioning there to John, that if you have questions, you can put them in the chat and we will sort through them when we get to the end of John's presentation.
Okay, how about that? Are we, oh, sorry. Do we have slides?
We're taking a look at your desktop there.
Oh, there we go. How's that?
Well, we're not looking at your slide view. We're looking at your notes view.
Oh, that's not good.
Want to swap displays.
Thank you. I'm not seeing. Oh, it does this sometimes. Where is the swap displays? Oh my gosh.
The curse of multiple screens.
Yeah.
Should be right across the top of your notes page.
Let's try that. Did we get there?
Looking at you.
No, okay, it's not
So you might not be sharing your screen at this point.
Yeah, you believe I do this all the time. It's something wrong. Something is wrong here. 1 second. Let's try this again. All right. Share screen. Desktop 2. Share.
All right.
But we're
Got your
not.
slides.
We there yet? No?
I see your slides. You might want to go to your presentation mode,
Right.
but we can do it from here if you need to. Okay, that's where you're going to see swap displays. I can see it.
Again. Sorry.
You're good.
John, I'm happy to pull the slides.
There we go.
Looks good. You got it. Yep. Thanks.
We got it finally. Sorry. Okay.
Good job.
So this is and we got full screen now? You have full screen slides?
Yes, you're
Great.
you're good.
Okay. So this is a great counterpoint to what Molly said, who did a great presentation, by the way. And I love the title of this talk that the Coastal Society's picked, the Art and Science. And you're going to see that really it requires a little bit of both here, because as Molly pointed to, there's many different projections. And the projections are changing because things are changing dynamically. And while we can study changing Atlantic meridional overturning currents and things like that, the question is, how do we design for the future? I want to kind of zero in some very plain language and help you look at a few points of clarity versus confusion. We tend to talk about a climate change problem. And I like to suggest at the start, we think of this as reducing the greenhouse gases, which is of course a very current topic, being resilient to the kinds of events, particularly flooding, that we can get now, and then adapting to something particularly like sea level, which is not going to rise that quickly as a global average, as Molly pointed out. And so we need to think of climate change really as 3 problems requiring 3 solutions. The problem with sea level, again, just to look at this at a very simple level, I'm going to give you a different perspective on the same data. Whereas Molly looked regionally or locally and up to 10 or 20 years and occasionally out further, I want to look at this globally and look at the big picture of where this is headed to help balance out the choice of which of the 5 projection models do we look at. The problem is Greenland and Antarctica. If you want to look at where the world's ice is, that's just, well, I'll come back to that in a moment and drill down on that. You may be aware that NOAA released its latest sea level report just a few weeks ago. And in that, it talked about by 2050, we could get 10 to 12 inches as the global mean average sea level increase. By the end of the century, 78 years from now, it said we could get 2 to 7 feet, again, depending on which model or which assumptions you want to put into the models. Similar to some of the graphs that Molly showed, if you look at temperatures or sea level, and there's a lag time, but one follows the other because of ice sheet melting, there is an up and down pattern. There's a general trend upward. And this has been going on now for the better part of the last century. If you, again, different depictions of abnormally warm versus abnormally cool temperatures, when we tend to see cold periods in the northeastern United States, we may not be aware that it's extra warm up in the Arctic. And in fact, last week, you may have seen headlines that we had record temperatures in both the Arctic and Antarctica, 50 degrees above normal. The second thing to point out as context here in framing is that we talk about coastal flooding. Coastal flooding is a combination of storms, rain, and we're getting heavier rainfall at the same time that we're getting more droughts in the world. That's with a warming planet. We get runoff coming downhill, so you have to look at elevation, extreme tides following the daily, monthly, and up to 19-year tide cycle. Those things all affect localized flooding. And then there's rising sea level, which is more like a drip filling the bucket that's really hard to see on its own. But as sea level rises cumulatively year after year and accelerates, which I'll show you, it means that when we have extra high tide flooding, that the extra high tide gets even higher. And then coastal erosion is often lumped in with issues of flooding and sea level rise, but is actually somewhat different in nature. We know what happens when storms hit shorelines. We are seeing signs of even historic houses like this one that's 100 years old. They didn't build that dock underwater, and there is no subsidence in this location. It happens to be Fort Lauderdale, but the water level is getting higher and higher and putting docks regularly and predictably underwater, even on clear days, blue sky events. Notice cars on the right here and boats off in the distance, and a no wake sign on the street. They put this out in a neighborhood in Fort Lauderdale to warn people not to drive their cars so fast as to spray salt water on the other cars. It's a sign of the times. This happens regularly, and then they go to take the signs down when the flooding has happened. But the big thing is sea level, and that's what we're here to put into bookends and look at the art and science. And what we do know about sea level rise, as Molly made the case, is that it's accelerating, it's unstoppable, it's actually somewhat unpredictable, hence the 5 different models and projection lines that people look at, and certainly the scientists look at, but kind of confuses the public and the engineers in terms of what do we design for. Sea level rise is essentially permanent. For centuries, probably 1,000 years, the planet will not be cold enough for the ice sheets to expand, which would be required for sea level to fall at a global level. So sea level rise that we're seeing today is essentially permanent. Sea level rise will worsen those flood events, which could happen next month. But sea level rise is slow, as again, you've already seen. This is a graph, it's in my book, actually either of my books. It was done with the help of Dr. James Hansen, a very prominent climate scientist. And it shows 400,000 years of 3 things: carbon dioxide, a greenhouse gas in green, global average temperature in red, and blue is global sea level average. Again, global mean sea level, as Molly referenced. So looking at the big picture, what's interesting is if we see the red line, 400,000 years left to right, global temperature has cycled through what we call the ice ages. It's been happening for 2.58 million years. We know that very well out of geologic history. And the difference from the average global warm period to cold period is 5 degrees Celsius or 9 Fahrenheit. And you can see it follows a rather regular repeating pattern. As the planet warms, the ice sheets melt, and I'll show you that in a moment, but sea level rises. So the blue lines and red lines move together. The red line and the green line move together for 2 different reasons. When the planet's warmer by geologic forces of what we'll call the ice ages for now, the oceans release carbon dioxide. When we put extra carbon dioxide in the air, which is what we're doing now, we trap heat in the ocean by a different principle of physics. So there are 2 different reasons why the red and green lines move together. But what's interesting is that these lines follow a predictable pattern. It's actually been going on for 2.5 million years. I'm showing you 400,000 years here to show you multiple cycles to kind of see the repetition of the natural warming and cooling we call the ice ages. And to realize that all 3 lines, carbon dioxide, temperature, and sea level, move together in large periods or long periods of time at a macro level. And the problem is now that is shown in the upper right in the circle. Carbon dioxide, of course, is shot through the roof and is at about 420 parts per million, where its normal bounds were 180 to 280. And the planet's warming, as we're seeing, and the ice is melting and sea levels rising. I need to speed this up, I think. When we look at the Arctic, it's warming 3 times faster than the global average. Again, as Molly alluded to, global means are interesting and very useful statistically, but we have to kind of look at what's happening in different parts of the world. And the problem in the Arctic is that the excess temperature is tending to go there at a ratio of about 3 to 1. The melting sea ice doesn't affect sea level for a reason I'll just show you in a moment, but of course, we're concerned about things from polar bears, but as the bright white goes to dark blue, it absorbs more heat. The huge icebergs coming off of Greenland are indicative or reflect the excess warming that's happening, and things are happening pretty quickly now. What's interesting about these giant icebergs is like an ice cube in a glass shown there, just for reference, about 10% above the surface. We talk about that, the tip of the iceberg. When ice is floating, whether it be ice cubes in a glass or icebergs, it doesn't affect the level of liquid as it melts, which is surprising and counterintuitive. You would think that the 10% of the iceberg sticking above the surface would add to water level. It doesn't, because ice is less dense than water. So the point is that once ice is floating, either a sea ice or a giant iceberg, it has no effect on sea level. The effect is when you put the ice cube in the glass, or when the glacier breaks off into a new iceberg and it falls, it calves into the ocean, or when meltwater from ice on land gets to the sea. Those are the two primary reasons why melting ice on land adds to global sea level. And then there's thermal expansion of seawater, which I think Molly referenced. So the problem for sea level, looking ahead, is that Antarctica and Greenland hold 212 feet of sea level if they were to all melt. They don't melt quickly. And in fact, as we increase greenhouse gases, the planet's warming. It takes a while to melt the ice sheets, which is part of the reasons it's hard to precisely or scientifically predict the rate of sea level rise as we get into mid-century. To give you an example of what happens with the ice age change of sea level, which goes up and down about 400 feet, we know the shape of Florida today. Sea level 20,000 years ago, during the peak of the last ice age, was 400 feet lower. So Florida was twice the size. And at the last warm spot, 120,000 years ago, sea level was 25 feet higher, and Florida is about half the size. Now, this could be done in other states as well. The reason for that is the ice age sheet, here it's shown in that cartoon movie, Ice Age Part 2, the meltdown. But we had 2 miles of ice, as we know, and as the ice melts, then sea level does rise, because that's ice on land. To wrap this up, because I want to allow time for questions here, but looking in cross section at sea level since the last ice age, when it was 390 feet or 120 meters lower, it did not rise smoothly. Sea level rose in spurts. Those 3 blue arrows are inflection points, or reflecting what we call meltwater pulses, which is large scale sudden melting of the ice sheets in the poles. And then sea level speeds up. So it's risky to predict the future or project the future with sea level, because we know that the 2 miles of ice that's on Greenland and Antarctica will not melt smoothly, and there will be points of collapse. And we think we're seeing it now. In fact, you may have noticed that East Antarctica had this large ice shelf collapse last week. We weren't expecting that in East Antarctica. Things are happening very quickly. But following this graph, it shows that sea level got to the present level about 6,000 years ago, which is pretty much human civilization. And that's what's fooled us into thinking that sea level is stable. But if sea level is going to change, the shoreline is going to change. And that's the real takeaway we've got to think about. We've assumed that sea level was stable. We measure things above and below sea level, but sea level is moving. So it's not a good reference point. And as sea level rises, of course, the shoreline moves inland all over the world, for not just Florida, but 24 US states and 140 nations. Sea level is not only rising, again, as Molly showed, we're saying similar material from different perspectives here, but I think in a good complement. Sea level for the last century rose about 1.5, 1.7 millimeters a year. That's very small, less than about 1/20 of an inch. But since we've had satellite data starting in 1993, the rate has more than doubled. It's over 3 millimeters a year now. And in the last decade, it's about 5 millimeters a year. It's that change in acceleration of sea level rise that should concern us. Because just like the pandemic, when things get into exponential growth, they will surprise us. And small changes of like interest rate on a loan, if you will, or a mortgage can have big effects. Well, the same thing with pandemics, and the same thing with melting ice and rising sea level. The past no longer predicts the future. So when you look at this big chart of 400,000 years, and it's on my website, by the way, and again, it's in my book, but I think you'll see here that we're tempted to think that the patterns all stay parallel, and they do, except that now we've got this huge change in greenhouse gas, which is turning into warming, which is turning into sea level rising. But the other thing that's worth noting here is that after the 20,000 years of rise, following the 80,000 years of fall, is that just at the last high water mark, by the natural cycle, without human effect, sea level was 25 feet higher than today. So I would contend that we've got to think bigger, and we really can't be looking at 5 different models and taking the median as people are inclined to do in the face of uncertainty. We have to realize that even without extra warming, sea level could be 25 feet higher, as happened 120,000 years ago, that all the signs are that things are exceeding the models, and that just as we wouldn't plan for an average hurricane, we shouldn't plan for average sea level rise. We should do the opposite. We should plan for higher scenarios, because it's going to be the most challenging effect of all to start planning for sea level being several feet higher and then some. So to recap some points here, again, we should try and slow the warming as much as possible. We should plan for resiliency, which is flooding that could happen soon. We also need to plan for adaptation, which is different than resiliency, because adaptation is to things which we don't even see yet, like higher sea level being 5 feet higher or 2 meters higher. And that it is unpredictable. And that's just the nature of it, because you can't predict how the giant ice sheets collapse. But just again, as a point of reference, I happen to live in Florida, but it's an easy state to use as a graphic illustration. Even 1 meter, 3 feet of sea level rise would not put the state underwater, as is commonly asserted. It would put some important areas like the Florida Keys and Miami and Fort Lauderdale in some real distress, as well as all around the state. But Orlando's 80 feet above sea level, Tallahassee's 200 feet above sea level. We must get away from thinking simplistically that sea level is going to put Florida underwater. First of all, it's not going to happen quickly anyway. We have decades to begin adapting, but we've got to get aware, and we've got to communicate better. And there are opportunities to re-engineer both landscape architecture and design and floating structures. But here's from a town outside of Hamburg, Hafen City, where they have terrible flooding routinely, and they've designed for it, and it's a wonderful, livable city. But finally, we have to wake up to the reality that while there are tides and there's rainfall and storms and erosion, sea level is a new and unique threat. And after 6,000 years of stability, it's rising, it's accelerating. It is hard to predict where it's going to go. I think we should be cautionary. But thinking of future generations, as reminded by this picture, we need to rise with the tide. It's going to get higher and higher. And with that, I'll turn it back to Whitney.
Thank you, John. Thank you. That was great. Thank you both for wonderful presentations. Very timely, very informative. And we do have a number of questions already in the chat. So I'm going to start right with them and just run through them in the order they came in. So the first is kind of a policy-oriented type question. How can we encourage local and regional plans and planning efforts when oftentimes elected officials are focused on their shorter terms of office? And we hear this a lot. This is, I think, an issue at every level. And let me turn first to Molly and see if you have any suggestions for how we can get our elected officials to focus on that longer term timeframe.
So I will say, in my experience, elected officials are concerned about the things their constituents are loudly concerned about. And so if people are asking questions of them about how these long-term resiliency plans are going to work, then the policymakers have a better reason to address those. It is very hard to invest dollars today in something that'll be a problem 20 years from now. So, having that ground swell of support is really important.
Thank you. Thank you. John, did you have anything to add to that?
The only thing is, you're talking about 30 years, which to most people sounds like a really long time in the future, but it's a home mortgage length. And so we tend to think of 30 years, it's a generation certainly, but I find it's the sweet spot, because you can't see sea level rise as a real problem in 10 years, okay? Because it's quarter of an inch a year. But 30 years, mid-century, even according to the NOAA report, we get a foot of sea level rise as a global mean average. That's a problem, okay? But putting that relevant to people and saying that's not super far in the future, that's just the payment of your mortgage. Is your house going to be, have value? So I like to think of 30 up to 30 years as kind of the short term, actually, but it's a period that resonates with people and also allows us to see a change in something like global sea level.
Mhm. I will say I agree with Molly that we've seen in Florida, and John, living in Boca, you're probably familiar with this. It was really a citizen initiative that created the Southeast Florida Regional Climate Change Compact, and which really was an effort, a citizen-driven effort that brought so much attention to that. And I think ultimately resulted in the programs that the state of Florida has initiated, and where they're now, very focused on adaptation, which, has it's good to focus on adaptation. There are other things you could focus on as well, but they're putting resources into the problems that the local communities are experiencing. And I think it's due in large part, as Molly suggested, to that pressure from constituents.
Mm.
So, yeah. Okay, let's see. Steve asked a question, I think, based on your red, blue, and green graph, John. He says, it appears geological temperature and sea level rise increase has at times preceded carbon dioxide increase. If that's true, how does that affect our understanding of CO2 increasing prior to corresponding temp and sea level rise?
Sure, good question. It's true. And that the warming and cooling we think of as the ice age cycles, which again is roughly 100,000 year cycle and been happening for 2.5 million years. That has nothing to do with carbon dioxide. That's driven by an orbital variation, mostly the elliptical orbit around the sun, but also the tilt and the wobble. So those three things are combined for the Milankovitch cycle. And that really is the trigger for the ice age. So when the planet's warmer, it releases carbon dioxide, which is why the temperature precedes carbon dioxide in the geologic history. Now we're putting carbon dioxide in the air, which was proven in 1859 to trap heat by John Tyndall in London at a demonstration, and it's easily proven. And because carbon dioxide traps heat, so now we have the heat going up before the carbon dioxide and before the ice melting and so on. So yes, that's a very astute observation, Steve.
Yeah. So once again, people have flipped the script.
Yeah.
Yeah. Thank you. This has been a really interesting piece of this whole discussion today is how many different forces there are at work that are bringing these changes to bear, not just, I guess they're all sort of derivative of the carbon dioxide increases, but the gravitational pull of the ice caps, of the ice sheets, and the Gulf Stream changes to the Gulf Stream, all of those forces. That's been really interesting to me to hear from you all about how all of those different things are contributing. Can either of you speak to how much those kinds of factors contribute to the estimates that NOAA provides or that the IPCC provides?
Well, again, if you're looking at one particular place, whether it be Virginia or Florida or Boston, it doesn't matter where, you need to take into account subsidence and uplift and all the current changes and all of those things to say what's going to happen here, during the next year, or if I'm going to design a new house or rebuild a house or something like that, or infrastructure like roads and water treatment plants, you need to look at there. It's easy to overcomplicate this, though. The fact is the planet has had sea level change 400 feet repeatedly. And obviously we are not even beginning to plan for 10 feet of sea level rise. We have to think radically now, I believe, because in the 6,000 years of human civilization, sea level has been pretty stable. Even if we stopped emitting all greenhouse gases today, if we burn no more coal or fossil fuel, the heat that's in the ocean is going to cause the ice to melt for centuries. We've warmed the oceans. I kind of skipped over that to keep this simple. But that's really the bottom line here is at the current temperature, no matter what we do to slow the warming, we're going to have ice on Greenland and Antarctica melting and sea level rising. So it's not a matter of if sea level rise, it's when. And if you don't know whether it's going to rise 3 feet or 6 feet, what's the smart thing to do? Would you build for 4.5, or would you build for 6, knowing it's going to get there and continue beyond that at some point? We have to think different, I believe.
Right. I want to mention just briefly that we are at time for our session today, but the speakers have all agreed to stay on. So anybody who wants to stay with us can continue the discussion. Molly, did you have anything? I just was asking about all those different forces that were discussed and how much do they contribute to NOAA's estimates or IPCC's estimates?
Yeah. So the different forces and processes contribute differently when you're looking at local sea level rise to those estimates. For global sea level rise, they all contribute. It's just one number. So it's the sum of all those different processes happening together. But when you start to get local, then the effect of each process changes, depending on where you're located and what's the most important process happening at that point and at that time.
Mm-hmm.
So at one point, Galveston, Texas was sinking 10 inches a year due to high groundwater withdrawal. When they stopped that subsidence slowed substantially, right? So you actually see a change in the sea level rise record there, reflecting that.
One other question in the chat that's sort of related. Do process-based models currently account for feedback loops of sea level rise, increasing greenhouse gas emissions? I'm thinking particularly about emissions from ghost forests.
Yeah, so there is some consideration of feedback loops that look at, but they on big scales. Okay, so they look at effects of things like carbon fertilization. So plants actually photosynthesize more when there's more carbon in the atmosphere available for them to use for photosynthesis. So as carbon increases, they actually take up more carbon. It sounds like weird, but this is how it works. And that carbon can be stored in the ground. And so there is some consideration of these type of feedback loops in the models, but these are on a global scale. And so the numbers being put into them are very big. And so where we know that emissions from ghost forests and things are actually very local, and we don't have particularly good numbers on them, I don't think the ghost forests are actually included right now in any of the models, but they would be hard to include, I think, is really my point, because they're happening on such a small scale when you look at the surface area of the globe.
Great. I want to just say real quickly that Ashley put in the chat a link to a survey, a feedback survey. If you all wouldn't mind visiting that link when we're finished with our discussion and letting the Coastal Society know how much you loved today's webinar, that would be awesome. Okay, here's a good question for both of you. Any thoughts on geoengineering strategies?
We've been geoengineering the planet since we hit the industrial age. And while it's something to be very wary of, we are at a point where we will do geoengineering. It's going to be unavoidable to try and cope with the effects and slow the warming, but it's should cause deep concern.
That's a good perspective. I kind of share your perspective. We've engineered our way into lots of problems, and so Molly, what do you think? And maybe we should, maybe Molly, you could mention what geoengineering is.
Sure. So, well, geoengineering is a really broad term, and I was actually curious what the person who put it in the chat was imagining. So it can mean actually trying to change the atmosphere with, natural processes, basically. It can also be used on a much smaller scale to mean beach nourishment or using natural geological features to deal with sea level rise. There's a lot of interest in it on a smaller scale. It's being used in almost every resilience plan I've seen in some form or another. And in two respects it can be good. Okay, so one is it buys time. It is not a solution though. Okay, so it's buying time. You're moving the water further back off your coast for a period of time. You get less wave impacts when big storms come in because there's a beach to help break the wave energy. But it also provides habitat. It provides undeveloped shoreline. So it has these like broader impacts, but it is not a long-term solution.
Well, let me clarify. So I never thought of beach renourishment as geoengineering, but fair enough. Let's just leave that. I won't dispute that. But to clarify, the geoengineering that I think Whitney is referring to at the global level, it breaks into two parts, either what they call solar radiation management to try and slow the warming. And the other one is carbon capture and sequestration to try and take out the carbon dioxide that's in the air. So most of the global geoengineering, not the local, beach protection and things like that, that Molly was referring to just now. There's more and more study about that because of the concern that as the temperature increase gets faster and faster, which it will, because of the greenhouse gas that's already up there, that we're going to have to do something to not only deal with the temperature, but also sea level rise as the ice sheets melt. And so at the global level, it's reducing the heat or getting the carbon dioxide out of the air that's already up there.
Well, let me offer, the person who asked was Christopher. Let me offer for Christopher to come off mute and see if there's a clarification that he'd like to offer for his question. Are you still with us, Christopher?
Yes, hi everyone. Yeah, what actually piqued my interest in this was a recent article actually by a well-known science fiction writer saying that it's been proposed lately to try to actually extract meltwater from the bottom of the ice sheets, that we actually have the technology to do that, that we could actually utilize the oil industry and use their extraction methods to try to extract the meltwater, because it's that meltwater that creates like a lubricant to allow the ice to slide in to the water. So, but John was actually mentioning what I was referring to, though, the solar, the aerosol, but I think we're going to be forced into that situation.
So that's a really interesting approach I have not heard of. Thank you for sharing that.
Sure.
Yeah.
I think it's crazy, but that's okay. Yeah.
Well,
Kim Stanley Robinson, the science fiction writer.
There's a lot of wacky ideas out there. We have to get fairly serious. The coastlines, it's great to talk about to the coastal society. The coastlines of the world are just starting to change. We ain't seen nothing yet.
And, speaking of that, another comment that was in the chat here is a thank you from London, England. Peter says that they have the Thames barrier there, and it looks like it's gotten much more use recently, and they're beginning to think about next generation defenses. What do you see as the outlook for really big scale defensive moves like that? I know that the Army Corps of Engineers recently proposed humongous floodgates in Biscayne Bay to protect the city of Miami. Didn't go over real well there. So what's the outlook for solutions like that?
Well, a couple of thoughts quickly. So even the Dutch, who did some great engineering around the same time as the British, the Thames barrier gates were put in, they weren't planning on more than a foot or so of sea level rise. Now they realize all of their plans have to be rethought in terms of the scale of what really could happen, multi-meter up to 10 feet of sea level rise this century. We need to think bigger. And as the floodgate, you talked about Army Corps of Engineers proposal for Miami, even if you put a steel barrier around Miami, it's porous limestone. The water will just come up in the middle of the city. So while a seawall or a gate can be a surge barrier during a storm, which would have some benefit, it is not a benefit against sea level rise, because as sea level rises, it will just go through that porous rock and come up miles inland behind the barrier.
Molly?
Yeah, I mean, I would concur that in general, these big engineering solutions are buying time again. And so they're pushing the decision down the road, which is okay if in the meantime you use that time to find a more permanent solution. But all of these structures, so the Thames Barrier is a great example. It is already in a redesign process because it's not high enough for the next 20 years to affect it. So, they're very expensive. We invest a lot of money in them. But we're not going to invest money. We're not going to build, a 35-foot wall or 40-foot wall because that is an outside possibility, right? So, so really the way we use them, we're buying time, and we need to use them, I think, very intelligently to make decisions while they're in place, and also not to consider areas behind them protected and therefore develop them as if the water was not going to end up there.
Yes, isn't that that would be a key message? Yeah, we're not creating safe zones necessarily. Yeah. So Adrian just asking, after we get to this question, I want to invite people to use the raise hand function. There's a small enough group left here that if you want to raise your hand and then come off mute, we can ask any more questions. But Adrian asks, what do you think is that permanent solution? Only landward migration and managed retreat, or is there a permanent solution? Well, let's start with you.
I would say unless we significantly manage to slow the rate of sea level rise, the only permanent solution is to eventually move out of the coastal plain. I mean, the areas that we live in, and I don't live anywhere near the water, but you can find whale skeletons where I live in Williamsburg. It was underwater at one time. If sea level rise continues to be underwater, the question is when. That's will it be in probably not 100 years, a fair amount above sea level, 200 years, okay? So yes, long-term, that is the permanent solution, or it's to live on the water. But yeah, it's the timing, I think, that's more the question than the will it happen.
Mm-hmm. Mm-hmm. John, any comments on that?
Again, we have to be realistic that even if we went to zero emissions today, the oceans have already been warmed 2 degrees Fahrenheit, 1.1 degrees Celsius. Okay. The goal of the climate conference is to stop the warming at 1.5 or 2 degrees Celsius. Okay. It's inevitable we're going to warm some more, but even at the current level, sea level should be 10 or 20 feet higher based upon the historic ratios. So it's tempting to bury our head in the sand and be denialists and hope for some magic solution, but it just doesn't add up. That, again, by nature, sea level was 25 feet higher 120,000 years ago. We should have that as our target at a base, knowing it could take centuries, but we got to think differently about the coastline.
Right. Thank you both so much. I don't see anybody with a raised hand in the participants list. And Ashley, if you do, and I'm wrong, please let me know. But I'll just take a minute to remind you to please do the survey that's in the chat, link in the chat. Ashley posted it a little while ago. And thank you both so much for being here. And we really all appreciate your wisdom and your information. Steve, any last comments from you?
I want to echo that gratitude to John and Molly, and you as well, Whitney. It's been really informative, and I certainly learned more than I expected, honestly, and we've had a great turnout, some great questions, so that's much appreciated. Wanted to mention, and Whitney, we spoke about this, this is such a big topic that we realized we couldn't cover everything in one session. We are thinking of having a follow-up session in a couple months, maybe 3 months, to bring a couple folks back. And now that we have the big picture about the science and the trends, to look at perhaps a little more near term, what regional types of solutions are being implemented, and perhaps give some folks some ideas about in the near term and the local term, what they can do to adapt. So stay tuned for that. But otherwise, again, great conversation. Appreciate everyone's time today.
Thanks, Steve and Ashley, for making this happen too.
Yeah, thank you. And thank you, Whitney, for the great moderating.
Yeah.
My pleasure. Thanks, everybody, and have a great rest of your day.
Great. Thank you.
Two. Bye
Bye,
all.
everybody.